This talk will be given by my new student. I hope you agree she's very cute. I'm sending you by the chat the name of the species. She's a redneck wallaby, 7 months old and orphaned, so we're taking care of her. But anyway, let me now find a screen to share. So you know the ratio of A divided by B is less than or equal to the maximum degree in B divided minimum degree in A. I'd say that even your weakest students know that, except that's probably not true. But anyway, do you know this one? That size of A divided by size of B is the maximum over edges of the degree of the B end divided by the degree of the A end. When I tell this to people, that I'm often met with disbelief, but let's prove it because it's very elementary. You take your two sets and you give a weight to each edge, which is reciprocal of the degree at each end. Every edge has got a left weight and a right weight, according to the picture. Now you can see that the left weights add up to the size of B and the right weights add up to the size of A. And yet for every edge, the left weight is at most alpha times the right weight, where alpha is the maximum ratio. So what we're going to do is generalize this simple result, and this is never weaker than the original result, and sometimes stronger. One of the things that switchings is used for is to bound the tails of distributions. And in the simplest case, we have some sequence of classes of things, graphs or whatever, defined by some parameter. And what you want to do is to bound the tail. So the small end of it, you want to find an upper bound on the size of that compared to the big sets, or maybe compared to everything. And if the picture looks just like that, it's a very simple thing. You just apply the ratio to each pair in turn and multiply all the ratios together. However, in a more complicated case, you might not have such a simple picture. Say, for example, that the parameter is the number of triangles in some family of graphs. It could be that you can make a switching which removes exactly one triangle when the number of triangles is not very large. But if the number of triangles is very large, it might not be possible, or at least not easy, to find a switching that neatly removes just one triangle without removing any others at the same time or creating others. So in general, you don't have a picture as simple as that. You have your switching operation, which is some small operation on the object, might move around between classes in some more complicated fashion. So each of the nodes in this graph is some class of objects, and the arrows give us trajectory of some switching operation. So the problem is now to bound the relative sizes of different sets of classes, given some information about the switchings. For example, you might want to know what is the maximum possible value of the number of objects in the right four classes divided by the number of objects in the left four classes as a function of the parameters of the switching. So what parameters? Let's choose some. Suppose we have our classes are defined by some parameter theta, and let u of theta be the class of objects with the given theta, and n of theta is the number of objects in the class. Let G be the directed graph that's got the classes as vertices and edges that indicate trajectories of a switching.
Brendan,
now suppose we've got
a question. Yes. Can you define switching for us, or tell me what it is?
It's just, at the moment, it's just a relation. So you have an object, you apply a switching to it, and you get something else.
Okay.
I'll give you examples, but it could be moving an edge to a different place if you've got a graph, or taking off two edges and putting them somewhere else. Or if you're working with a Latin square, you might interchange a few entries in the square while preserving the Latin property. It's a very general concept. It just means some operation. In practice, it means some small operation which changes a graph in some, or changes the object in some small way while maintaining most of it, but that's not necessary for the theory.
That helps me, thank you.
Probably should have given examples before I went into the theory. Okay, now suppose you have some functions in and out, and the meaning is that every object with parameter theta has at least out of theta switchings coming out of it. This one I forgot to write on this line that this is only if theta is not a sink in the graph. You can have sinks in the graph where no switchings come out at all. And the function n says that every object with parameter theta has at most n switchings into it. So those are the input parameters. A variable is s of an edge theta to theta prime. It's a directed graph, of course. And this is the total number of switchings that consist of an object of parameter theta and a switching that takes it to an object of parameter theta prime. So the definitions of in and out give us these inequalities. So the sum of all of the out neighbors of theta, the total number of switchings coming out of theta is this summation here. And that has to be at least out of theta times the number of objects in theta. That's just the definition of out. And this is only if theta is not a sink, otherwise you don't have this inequality. And the other way around, if you sum over all of the switching coming into theta, then that's less than or equal to the size of theta prime. This is all the object switchings coming into class theta prime. It's at most the size of the class multiplied by n of theta prime. Now, as well as this, we're given two sets x and y of theta values. And what we want to find is an upper bound on the number of objects in the class y divided by the number of objects in the class x. So x and y can be any sets of theta values, even like just one class or everything, or they might overlap with each other, and it doesn't matter. Of course, n of z, where z's a set of theta values, is just the sum of the class sizes for theta in z. Okay, so now we generalize the example of two classes to maximum over edges rather than maximum over vertices. We can do the same thing here. Alpha of a directed edge is in of the head divided by out of the tail, and that's an input parameter, and the variable s is divided by the in of the tail to give us the new variable t. And we just make those changes, and then we get this new set of inequalities. You can at most get relative class sizes out of these inequalities and not absolute class sizes, so you might as well normalize it. We'll normalize it so that the total size of x is 1, and our problem is then to maximize the size of y. So we've normalized the number of objects with theta in x to be 1. We want to upper bound on the number of objects with theta in y. And we can take this as our new problem statement and forget about out and in. And this allows us some extra generality to the way I started with the out and in functions. Now this is, of course, a linear program once we normalize it. but it's got a special form, and that enables us to find a fairly explicit solution. Villefaq and I solved this when G is a cyclic graph, except for loops are allowed on vertices. But Mathieu Hashimnejad and I solved it for arbitrary directed graphs G. And I'll show you what the solution looks like. So we forget about cases where the solution's infinite. You know that when you have a linear program and the solution's not infinite, then the optimum occurs at some vertex of the polytope divided by the inequalities. So you examine the nature of these inequalities and figure out what the vertices look like, and you find there's 6 types of vertices. And these pictures represent the edges in the graph for which the variable t of the edge is not 0 and has to be one of these 6 shapes. Moreover, for any particular one of these, the solution is defined precisely. I haven't written it down here, but basically the inequalities are satisfied with equality along these edges. And everywhere else, every other directed edge in the whole graph has got t of 0, which corresponds to s of 0 in the original formulation. So in general, you have to look at all the subgraphs of your graph that look like one of these 6 types, figure out what n of y is, and then choose the largest. Often in practice, your graph has a slightly simpler shape, enabling you to easily identify which type is dominant. And here's a case that occurs extremely often in practice. So this is a diagram of our graph. X is the base set that we've normalized to 1. Y is the set that we're trying to find an upper bound on. And the properties that are required are X is not empty, it doesn't intersect Y, it has to contain all the sinks, and also has to contain the tail, has to contain the tail of every edge for which the alpha value is greater than or equal to 1. And if the graph looks like that, then we can define the optimum like this. Define alpha of a path is just, of course, the product of the alphas along a path. And you take P, Y, X to be the set of all paths that they start in Y and end in X, but only the first vertex is in Y and only the last vertex is in X. And then P of YY is the paths that start and finish in Y, where only the first and last vertices are in Y. And the intermediate vertices aren't allowed to be in X, but they can be in the no man's land in here. And then you have this bound that n of y is less than or equal to the maximum of the PYX paths divided by 1 minus the maximum of the PYY paths. And you have to take empty maximums to be 0, which is slightly unusual. Let me do some examples. Suppose you've got an n by n chessboard and you've got k dominoes on it. And we'll put the dominoes on the chessboard in any fashion, whatever, but all configurations equally likely. So it's a uniform random distribution of dominoes on an n by n chessboard. And we want to know something about the number of 2 by 2 squares that are covered by the dominoes. So here's an example. Forget the color for a second. You know what a 2 by 2 square is? There's one there. There's, I think, 6 or 7 covered 2 by 2 squares in this picture. And as a switching, you can define it any way you like, but we'll define it here. We'll take a 2 by 2 covered square we'll take the domino that gives its upper right corner and we'll move it somewhere else. For example, there. We don't have to choose where we move it. It could be anywhere at all. In fact, we're even allowed to put it back where we took it from. So what happens when you apply the theory to this problem? Well, the number of ways of performing the switching is at most this expression here, 2n n minus 1 minus 7k times theta. So there's theta ways of choosing the 2 by 2. The theta is the number of covered 2 by 2 squares. So you can choose one of those in theta ways, and then there's exactly one domino covering its upper right corner. And then you just count how many places you can put it down, and it's most this 2n squared minus 7k. And when you do that, it decreases the number of covered 2 by 2 squares by at most 6, which is not hard to verify. And the nice thing and the interesting thing about this is it doesn't matter if you even increase it. It's possible to put this domino down somewhere else where the number of covered squares increases. It doesn't matter that that's possible, and it doesn't matter how much by that's possible. The only important thing is that it can't decrease it by more than 6. And we'll go back and go back to this. Here, this PYX corresponds to paths going from Y to X. The paths that start in X and end in Y, which would be increasing the number of dominoes, don't come into the answer at all. It's only the paths that decrease dominoes. Also, because the alphas in here are less than 1, that's the condition on X, which is up the top here. All the alphas in here are less than 1. You want to multiply together as few of them as possible to get the largest product, which means you want to take big steps. And in this problem, the steps have got size 6 because 6 is the maximum number of squares less caused by doing this switching. So you also have to get an upper bound on the number of inverse switchings, which means pick up a domino from somewhere and use it to create a new 2 by 2 square where the domino you just put down is the upper right corner. It's just the inverse of the switching, and that's at most 2k squared. So you now have the ratio of two things is the value of alpha, and you apply the theory and you get this nice bound here on the probability of there being at least m 2 by 2 covered squares as long as m is large enough, and has to be larger than 5, and it has to be larger than this expression here, which it can be big if k is very large, but usually it's small. So we used almost nothing about the structure of the problem. We just used some simple counts about how far downwards a switching can take us, and we don't care that it can also take us upwards. So here's another one that I just made up. We've got a one factorization of the complete graph given by colors. And let's suppose that all one factorizations are equally likely. And if you look in here, you find some 4 cycles with 2 colors. For example, there's a pink, red, 4 cycle there. And we want to find an upper bound on the probability that there's a very large number of these in our random one factorization. So what can we use as a switching? Well, let's take one of the edges of this 4 cycle, take another edge that's incident, which will have to have a 3rd color, and then the 2 edges arrowed give us a cycle. In this case, it's a pink-red cycle, pink-black cycle. So you follow pink, black, and you switch the colors along that cycle. It's another 4 cycle in this case, but it doesn't have to be, could it be arbitrarily long. could even be like a Hamiltonian cycle. So you switch colors along, that gives you another one factorization, and it destroyed the initial two-colored 4 cycle. So now you do your counting with that. And if theta is the number of two-colored 4 cycles, the number of switchings available is at least 2 times n minus 3 times theta. And the number of that, the maximum that the number of two-colored 4 cycles can be reduced is n times n minus 3. And inverse switching can be done in at most n times n minus 1, n minus 2 divided by 2. And then their theory tells us an upper bound, which I haven't written down, of the number of two-colored 4 cycles. And if the number is increasing with respect to n squared, it gives us quite a good upper bound, exponentially decreasing upper bound. Okay, so now in some problems, you have more than one type of switching. And so we've got in this 4 types of switching given by different colors. And this is not the same as just giving different alpha values to the edges, because you've got a different set of inequalities. You've got a complete set of inequalities for each color. In this generality, we haven't given a general exact solution, but we've got some very good upper bounds which have proved useful in practice. So that's the end of that topic. And next thing I'll mention is the use of switchings to estimate subgraph probabilities. There's 2 different ways of doing this. One of them is to use switchings to analyze configurations or pairings, and I'm not going to talk about that at all. What I'm going to consider is directly applying switchings to subgraph probabilities of graphs with given degrees. So the stuff in the past has been mostly done with these types of switchings. And the upper right edge is the one we're interested in. So if we want to know what is the probability that there's an edge where it's colored red, we can use the switching that swaps the figure on the left to the figure on the right and put that edge in and out without changing the degrees of the vertices. So in these pictures, the dotted lines are non-edges. So starting at the edge of interest, it goes out, in, out, in, out. It's an alternating path. Even this last one is an alternating path. It goes in, out, in, out, in, out. And you can switch along the alternating path. The last one looks strange, but use it in conjunction with the second one and you get better counting properties. I haven't got time to go into that. The first theorem of this nature I proved in 1981. I guess I did it as a PhD student. And this says that if you've got a random graph with degree sequence D1 up to, Dn, that is, and you've got some graph with degrees x1 up to xn, and you want to know the probability that your random graph contains x, then this is the expression, and it holds as long as the degrees are not too large. So this expression here, d max squared plus d max x max, has to be little o of the number of edges. Well, multiplied by the number of edges in x has to be little o of number of edges. This has been improved quite a few times since then, but I'm not going to survey it because Jane Gall's going to talk about this and related things in her talk later today. I put today in quotes because that's 4 a.m. for me. But I just talk about a particular new aspect here. Instead of graphs with degree sequence D, think of that as subgraphs of the complete graph with degree sequence D. Isn't any difference? Well, in the theory, we're allowed to take a few edges less than the complete graph, which means we're allowed to specify some edges that are forbidden as well as the ones we want. But the theory so far has not allowed us to take all that many edges away from the complete graph and still perform this calculation. There's also a bipartite one, which allows us to be, our supergraph to be a few edges smaller than the complete bipartite graph, but not very much smaller. So now, as part of a project to prove the Kim and Vu sandwich theorem for sparse graphs, together with Jane Gao and Misha, we figured out a way of doing switching within a sparse supergraph. Now here is our supergraph. Both the black and red edges all together are the supergraph S, and the red edges are the subgraph we're looking at, and it's got a given degree sequence. So we're only interested in subgraphs of S that have a given degree sequence, and we want to know some things like whether the subgraph has an edge in a particular place. So we look in a particular place, say where the asterisk is, and say that's our edge of interest. And we can't do any of the standard switchings here because when the supergraph is sparse, you can't find 4 cycles and 6 cycles to switch along, generally speaking. So, but you can use longer cycles. A plain cycle like this one will suffice. Again, it's an alternating cycle, but in this case, we're staying inside the supergraph all the time, and we're just alternating whether or not we're in the subgraph. So we've got black, red, black, red, black, red, black, red. It doesn't work if you restrict yourself strictly to cycles, but it could be any alternating path like this one goes black, red, black, red, black, red, black, red, and I repeated some vertices. That's okay. So switching here corresponds to an alternating walk in S, and repeated vertices are allowed, but repeated edges are not. And switching the subgraph along the walk keeps it in F, keeps it inside S, and preserves its degrees. So by counting the number of switchings forward and backwards, which is a messy problem, I'm not going to state the theorem because it would take at least 2 full slides to give the definitions and state the theorem. I'm just going to tell you that we've done it. There are some technical conditions. The subgraph of interest has to be sparse in S, and S can't be arbitrary. It has to be a subgraph of a yet larger graph, which is not much denser than S and is near regular and has good expansion properties in the sense of all except this largest eigenvalue are comparatively small. And these are quite technical if they're spelt out. The theory is very successful. The average degree of the supergraph only has to be at least polylog in size, and it can be anything up to the complete graph. And the theory works. It gives us some nice probability of an edge in a particular place. Okay. Last problem, linear hypergraphs. And this part of the talk has got 2 parts. One part joint with Fang Jian, and the other part joint with Mahdi Hashaminejad. So you know what a hypergraph is, and you know what linear hypergraph is, or do now. Linear means that no 2 edges have got more than a single vertex in common. So the one on the left is linear and one on the right is not linear. There's very little precise enumeration known on linear hypergraphs. If the degree sequence is specified and not too dense, then Blinovsky and Greenhill found a formula for the number of, doesn't say linear, but it should say linear in this sentence, the number of linear hypergraphs. Otherwise, there isn't any previous asymptotically precise enumeration that we know of, just some bounds. In particular, there didn't seem to be any earlier work on the number of R-uniform linear hypergraphs with given number of edges. So let's let L of R and N and M be the number of linear R-uniform hypergraphs with N vertices and M edges. Now, if you think about pairs of vertices, altogether there's N choose 2 pairs of vertices. Every edge has R choose 2, and you can't overlap edges by more than one vertex. So this is an upper bound on the number of edges. If you get an equality, you've got a Steiner system, but we're not going anywhere near that upper bound. Our condition is a more modest R to the minus 3 times N to the 3 over 2. R is allowed to be a function of N, and of course so is M. Okay, so I'll describe the main case of the proof where we have at least N over R squared edges and at most the upper bound that I just gave you. The first step is let's generate a random hypergraph with this many edges, not necessarily linear, and see what it looks like. Well, with high probability, it has one of these 4 cluster types. Our cluster is a maximal set of edges that are connected with respect to sharing 2 or more vertices. There's not supposed to be any of these except for single edges in a linear hypergraph, but here we've generated just a random hypergraph, and so we get some clusters. And the first thing is that there's only 4 types that are likely to occur with high probability. For each of these types, there's some number, and with high probability, we don't get more than that many clusters of that type. There's a different bound for each of the 4 types. No 2 clusters share more than 1 vertex. The maximum degree of the hypergraph is not very large. I won't tell you how big. And some other conditions about overlapping of clusters that are too technical to write in the slide. So we've got a whole lot of properties. I think there's 6 or 7 technical properties altogether that hold with high probability for a random hypergraph. So we exclude now all the hypergraphs that don't have these properties, and we're only excluding a small part of the space. We have to be careful because it might not be a small part of the space once you've only looked at the linear ones, which are also a small part of the space. But anyway, continuing. The second step is to use switchings to remove the clusters one at a time. Now, we haven't got any conditions on the degree sequence. We don't have to preserve it. We do have a bound on the maximum degree. We can remove a cluster by taking its edges and moving them somewhere else. You can, in fact, destroy a cluster by just removing one of its edges. But if you do that, you find that the counting doesn't work, because when you're estimating the number of inverse switchings, the number of inverse switchings depends on more information about the way the edges in the hypergraph are distributed, and we haven't got any information like that. So if you take all of the edges and put them all down somewhere else without creating any other clusters or destroying any other clusters, I guess you can't destroy any other clusters, but you're not allowed to make any others, then you find that you can do the counting reasonably well in both directions. There's a slight difficulty in that switching might take the maximum degree over the bound that you've made, but this can be dealt with a bit of effort. It turns out to be not a big problem, and we get an answer like that. Now, the binomial thing out the front, of course, is the number of R-uniform hypergraphs with M edges. So the exponential part is the probability that a random one is linear. We also found a formula that gives the probability of a specified sub-hypergraph appearing in our random linear hypergraph. Now, suppose we, instead of specifying the number of edges, we make an R uniform hypergraph in the Eders-Rainey style. You take a probability P, and then for each of the possible n choose R edges, you put them in with probability P. So what can we say about this family of graphs? Let's let M0 be the expected number of edges. And we need the same bound on M0 as we put on the number of edges before. So the first question is, what's the probability of it being linear? And this is an easy question. You just multiply by the probability of having given number of edges, sum over the number of edges. The maximum of the sum doesn't appear where you thought it would, but that's not a problem. The sum is easy enough to do, and you get an answer. I won't write it down. Question I find a bit more interesting. Suppose you do this random process and condition on the result being linear. So you just repeat generating random R uniform hypergraphs using edge probability P until you get a linear one. What can you say about the number of edges? And because the probability of being linear decreases very rapidly as the number of edges increases, the expected number of edges conditional on it being linear is less than without that conditioning. And this is the formula for the mean, and the variance is M0. Okay, I'm coming close to finished. This is, I think, almost maybe the last slide. So the second problem on linear hypergraphs is what happens if the edge sizes are mixed? In this case, we didn't allow the edge size to go to infinity, although we could. We just took a fixed bound, capital K, and we said, how many linear hypergraphs are there with M2 edges of size 2, M3 of size 3, and so on up to MK edges of size K? And the answer is like this. Again, the product in front of the exponential is just the number of hypergraphs altogether. So the exponential gives us the probability of one of them being linear. The method's similar. You first of all generate a random arbitrary linear hypergraph with the right number of edges of each size. You throw away those that have got unusual things like too many clusters. And then you use switchings to remove the bad things one at a time. It's a little bit tricky. In some ways, it's trickier than the previous problem because all edge intersections are more or less equally probable. An edge of size A can be intersecting another edge of size A with 2 vertices, or could be intersecting an edge of size B with 2 vertices. As you switch away each type of intersection, you have to keep track of the number of times edges of those sizes are involved in other intersections. But it all comes out in the wash finally, and you get this answer. To compensate for this extra trickiness, we didn't go as far. So we've only got up to n to the 4 on 3 edges of each size. And of course, there's only a constant number of sizes allowed. Okay, I think that's the end. So let's just say thank you for a wonderful conference.
Okay, let's thank our speaker. And if you look at the window with chat, you already get some questions.
Yeah.
If you
have
prefer
to find it.
you.
Okay.
So question from Rupeiksu. Is switching related to Markov decision process? Can switching be considered as a new pivoting rule for linear programming? I feel that since simplex method pivoting rule for linear programming has a similar flavor. We also mentioned the polytope vertex relationship.
Yes, I honestly don't know the answer to these questions. Obviously, yes, it is a finite machine model. It's not exactly the same in the sense that we're not generating anything. And the input is a lot of bounds rather than precise values. Otherwise, you'd have to solve equations.
So questions keep coming into chat.
Okay. Rupai, ask again if I can be more precise, but I'm not clear about the answer to your questions. On Haya's question about preserving the maximum degree, the thing is that you can't in general preserve the maximum degree. What you have to do is to show that the number of switchings that increase the maximum degree over the bound are small compared to the total. And you can in fact do that by an auxiliary switching, which changes the maximum degree. There's something I didn't write down in the very earliest slide where we said the ratio of two set sizes is the reciprocal of the ratio of the average degrees. So you can augment that by, on each side you have an extra set which is small compared to the main set. And these are the hypergraphs that have got degree which is over the degree bound. And if you show that those parts are small compared to the main one, you can still find good upper and lower bounds on the ratio of the sizes of the main sets. I don't know if I can explain it more without being able to write to you.
Are you answering high questions still? Or
yes, no, I'm reading Yuval's question, and I guess the answer to that is no. But what is the switching lemma in this question?
Hi, Brendan. So yeah, there's no connection to your type of switching. It's just there are a few opportunities in combinatorics where you're trying to bound the probabilities of varied events by comparing something to something else. So that's another case
Yes.
where it happens. That's all. I'm not sure that there's any connection. Apart from
Well, it would be interesting to explore connections if there is any.
yeah, there's also been recent work on by Nathan Keller and one of the students where also you have some kind of tail bound which are proved by some kind of modification process. So yeah, it would be nice to explore.
The wallaby's name is Snowy, by the way.
I have another question for you, Brendan. So the general theory of switching, the way how you describe it, is really about the ratio of sizes of two sets, right? So it's designed for equation problems where you count things and you want to understand the ratio of how many things in one set divided by how many things in another. What if we replace number by weight?
I don't think it makes any difference.
Okay, so the particular question, is it true that we still have these 6 type of vertices of polytope, or there might be some other types?
Well, if you take the objects in some of the classes and you just subdivide them into more objects, then all you did is just change the numerical values of the parameters. Isn't that the same as weighting them?
So you duplicate and count according to multiplicities.
I think it doesn't make any difference. When I said that n is the number of objects of parameter theta, it could be the total weight of all the objects with parameter theta. And I think it doesn't make any difference because the inequalities will be the same.
All right, so then we can think about it as a probability.
Yeah, maybe.
Like probability of one event with respect to another.
I think it has never been written down properly in the language of probabilities. And that might be a useful exercise.
I have a question. I don't know if I can sneak one in. Hi, Brendan.
Hi.
You proved the central limit theorem, and did you prove it by just the local limit theorem, by finding the formula and showing it's asymptotic to e to the minus x squared, or how did you prove your normality?
We actually found the point values of it.
Yeah, so local limit, that's great. That's very
Yes.
impressive. Wow.
Yes, it is a local limit theorem. It works quite far out into the tails as well.
Wow.
Right, do you have other questions for Brendan? How many wallabies you have currently in your house?
At the moment, we only have one. She's 7 months old and her mother was killed in a car accident. So we're taking care of her.
All right, let's thank Brendan again.
Well, thank you for the invitation.